To introduce myself quickly again for everyone who doesn't know me yet, my name is Glas. I'm a master's student at TU Munich, and I joined CWI in May this year to write my master's thesis here. So my thesis was supervised by Azim and Peter. And the title of my project is C3, Compressing Correlated Columns. And it's about exploiting column correlations for compression. So in the next 30 minutes, I will cover some background and motivation for the project, present our new C3 compression schemes and our compression framework, and then present the results. In general, compression schemes used in database systems can be separated into two categories. So we have heavyweight and lightweight compression. And heavyweight compression, also called general purpose compression schemes, for example, gzip, only see data as a series of bits and bytes, and they try to exploit patterns between these bits and bytes. So they can be used for any type of data, hence the term general purpose compression. In contrast, we have lightweight compression schemes, which look at data on the data type level. And they need all the values of the data chunk to have a specific data type, for example, integers, strings, or doubles. And the patterns exploited by these lightweight compression schemes are on the data type level. And these schemes offer faster compression and decompression speeds compared to general purpose compression. And these lightweight compression schemes are pretty ideal and also widely used for columnar database systems and file formats, where each column has a fixed data type already, and the values of the column are stored consecutively in memory and on disk. So this guarantees that each block of values all have the same data type and allows these schemes to exploit patterns also between consecutive values in one column. So given these two columns as an example, our typical lightweight compression schemes would consider each column individually and take a compression scheme which is most suitable for each of these columns. However, by considering only one column at a time, the lightweight compression schemes are inherently not able to take advantage of patterns between these two columns. So in this example, we can see that the values of the second column are exactly double the values of the first column. So we could compress the second column by removing it completely and remembering that we can recreate it by just taking the first column and multiplying it by 2. So this is one example of correlated columns, and we will see that there are many types of correlations in real-world data. So about related work, there is almost no existing research on exploiting correlations for compression. And we could say this project is the first to explore the potential of exploiting correlations for lightweight compression schemes. So there are 2 papers which have touched the subject, white box compression and Corbett. So in white box compression, we have logical columns which are deconstructed into physical columns by applying transformations which make the physical columns more compressible. The authors did explore the idea of finding correlations between physical columns and using them to improve compression, but they didn't explore this in depth. And the results also don't indicate how much compression ratio they gained by exploiting these correlations. Furthermore, we also want to explore the potential of exploiting correlations for lightweight compression schemes in general, and not just restricted to the context of white box compression. Corbett is a paper exploring compression of bitmap indexes. And the main idea is that if 2 columns are correlated in a way such that there's a direct mapping between values of one column to the values of another column, then the bitmap indexes of these columns will also be very similar or the same. And when XORing the bitmaps of 2 correlated columns, the result will be a very sparse bitmap, which makes the bitmaps more compressible using schemes such as roaring or RLE compression. So while the paper does explore exploiting correlations for compression, it only deals with the compression of bitmaps and not the columns themselves. So we designed new, we call them C3 compression schemes, to exploit correlations. And here's a quick overview of how they're designed. So every C3 compression scheme works on a pair of columns. We have a source and a target column. And each scheme uses correlations between the two columns and makes use of the source values to help determine the target values. And the schemes are designed to improve the compression ratio of the target column. So some C3 schemes do not change the source column at all, but some require the source column to be dictionary encoded, for example. And the overall goal for every C3 scheme is to be able to compress this pair of columns better compared to applying single column compression schemes to the source and target column individually. So we looked at correlations in real world data sets, and we designed 6 compression schemes to exploit these correlations. Traditionally, the compression frameworks using lightweight compression schemes have a set of different single column lightweight compression schemes. And our C3 schemes don't replace them, but we add them to the scheme pool. So both can be used in conjunction. So we are adding the ability to exploit correlations if they are present in the data. So let me start with our simplest C3 scheme, equality. So given 2 tables of a column which are identical, it's pretty clear that we can exploit this for compression by just throwing away the target column and storing only the source column. But even if there is a small amount of deviation, for example here, then we can store this as exceptions, and we can still benefit from the correlation. So in this case, the exception needs to store the index where it occurs. So here in position 0, 1, 2, 3, and also the value of the exception, so an A. So after applying this encoding, we leave the exceptions uncompressed, and the source column has been left unchanged, and it can be compressed with any single column compression scheme. So next up, we have numerical correlations. So given 2 integer columns, in this example, we can see there's a strict linear correlation between the values. So the values of the target column can be reproduced by applying a linear function to the source column with the slope and intercept 1. So in this case, the target column can be completely discarded, but to also exploit linear correlations which are not perfect, we also allow some deviations to occur. So these 2 are still correlated, but we need to store deltas as well. But these deltas are very small and can be compressed well with bit packing. And here again, the source column has not been changed, and it can be compressed with any integer compression scheme. Next, dictionary sharing. So here we have 2 columns which are suitable for dictionary compression. And this would be the output if we would dictionary compress each column individually. So we can see that there is an overlap between the dictionaries of both columns. Both dictionaries have A and B. So in this scheme, we detect this overlap and we merge the dictionaries and store this shared dictionary with the source column. And the codes for the source and target column are further bit packed as in a regular dictionary compression. And we leave the dictionary itself uncompressed. So this scheme does require the source column to be dictionary encoded, even if other compression schemes may be more suitable for the source column. So moving on to the one-to-one dictionary. So in this example, we have 2 columns with city names and airport codes. And here we can see that each city name is always mapped to the same airport code. So we have a one-to-one mapping. And if we dictionary encode the source column, we can use the codes as indexes for the 2 dictionaries, and we can recreate both the original source and target column using just these codes and 2 dictionaries. And in case there is a small number of deviations from this mapping, for example, a flight to Luton Airport instead of Heathrow, then we can store this deviation again as an exception. And these exceptions, for the exceptions, we have to store the index where it occurs, And in this case, we store the code, this number 3, to retrieve the correct value from the dictionary. So Luton is in position 3. So again, here we leave the dictionaries themselves uncompressed and the exceptions as well. And the codes for the source column are bit packed. So exploiting a similar correlation is our 1-to-n dictionary. And this scheme exploits correlations where the source can be seen as a categorical column and the target values are members of the categories. So in this example, we have shoes and phones as categories, and we have 2 types of products for each category. If we dictionary encode both columns individually, this would be the result. This scheme aims to scheme aims to improve the compression of the target codes here. So instead of having the target's codes up to the total number of unique values, so we have 4 unique values, so we need 0, 1, 2, 3. We can store the codes relative to the category. And since each category only has 2 products, we only need to use 0 and 1s. So in this case, if we still want to use these codes to access the correct values in the dictionary, we need to store an offset for every category, so for shoes and phones. And these offsets combined with these codes together can be used to use this dictionary and recreate the original target column. Yes, so by decreasing the size of these integer codes, they can be compressed better with bit packing. And yes, we leave the dictionaries and offsets uncompressed, and yes, both codes are bit packed. And finally, we have the dictionary frame of reference. So in this example, we have a column with authors and a column with the years of books they published. So J.K. Rowling published 3 books between 1997 and 1999, and Charles Dickens 3 books between 1836 and 38. So again, if we would dictionary encode the source column, we can assign a reference value to each source value. So for Rowling, we store 1997, and for Dickens, 1836. So now for each target value, we only need to store the delta with respect to the reference for its category. So this exploits correlations in which an integer target column has values that are clustered in separate distinct ranges based on a category which can be derived from the source column. And again, we leave the dictionaries uncompressed and use bit packing for both codes. So moving on, how do we integrate these schemes into a compression framework? So given a table, we start by horizontally partitioning the table into row groups. And each row group is then passed through our compression pipeline, one after the other. So we treat each row group separately. Now, going through each step of the compression pipeline, the first step is collecting column statistics. So we pass over every column in the row group and collect statistics, which include the number of unique values, the number of null values, and also the total set of unique values. And for string columns, we also calculate the total size of the unique strings. And we use these statistics in the next steps. So next, we compute the expected compression ratios for all of these single column compression schemes. So we loop over every column and compute the expected compression ratio for every applicable single column compression scheme. And we compute these using both samples and column statistics. We also use the column statistics to filter out any unpromising schemes. For example, if a column has too many unique values, it's pretty clear that it might not be well suited for dictionary compression. In the next step, we again compute expected compression ratios, but now for the C3 schemes. So now we have to loop over each pair of columns and compute the estimated compression ratio for every C3 scheme which is applicable. So the search space is quite large. It's O of n to the power of 2 times n, given n columns and m C3 schemes. So we use column statistics to filter out as many unpromising schemes as possible. And the expected compression ratios for the C3 schemes are also computed using a set of samples and column statistics. So after having computed all of the expected compression ratios, we now need to decide which schemes to pick. So for every C3 scheme, we compare the expected compression ratio to those of the best single column schemes for those columns. And only if a C3 scheme is estimated to compress better than the single column schemes do we consider the C3 scheme for further usage, and we add it to a correlation graph. So this is an example of a correlation graph where the nodes represent columns and edges represent C3 schemes or correlations between those columns. And the weighted edges in the graph contain the estimated number of bytes which are saved by using the C3 scheme instead of the individual single column schemes. We can see that multiple schemes may be applicable between two columns. And on this graph, we use a greedy algorithm to pick the schemes which save the most amount of bytes. So we can see while a source column can be reused for multiple schemes, each target column can only have one input edge. And we also don't allow chained correlations to avoid needing to decompress a long chain of columns just to access one final column. So now compressing a row group. After having picked our C3 schemes, the first step is to apply all of the C3 schemes. And here we need to take care of the situation where multiple C3 schemes share the same source column. Then we need to make sure that the source column is encoded and compressed in a way which satisfies the requirements for all C3 schemes using the source column. We also added a mechanism which allows C3 schemes to be reversed and undone. So if after applying a C3 scheme, we realize that it's actually much worse than expected, and even worse than using single column schemes, we can revert back to compressing only with single column schemes. And this is especially useful when we use low sample sizes, in which case the expected compression ratios of the C3 schemes are less accurate. So the trade-off we have is the overhead of reversing these C3 schemes and the overhead of using larger sample sizes. So after this step, all remaining columns which haven't been compressed are compressed with the best single column schemes, which are determined by the expected compression ratios computed previously. So to test our ideas, we wanted a C++ implementation, and we used the BetterBlocks file format as a basis for this project. So it's an easy-to-use code base with columnar storage and a row group-based compression, which is exactly what we wanted. And the row group size, which BetterBlocks uses, is a fixed tuple count of 65,536 tuples. And importantly, BetterBlocks also has a rich set of lightweight compression schemes, some of which are listed here below. We tested our implementation on the public BI benchmark. This is a user-generated benchmark with real-world data, and it consists of at that time, the 46 largest workbooks in Tableau Public. And we use a subset of 36 tables consisting of almost 2,300 columns. So what are the results? To first check how much compression benefit each of these C3 schemes can provide, we added each of them individually, and we tested them on a single row group and using the full row group as a sample. So this represents the maximum potential for each C3 scheme on this data set. And the compression ratio listed here represents the improvement over using only single column compression schemes. So for example, the first one, the 1-to-n dictionary, it improves compression by 20% compared to using only single column schemes. And here we can see also how often each scheme was used. So this gives us an idea of how often each type of correlation occurs in the data sets we used. So numerical correlations occurred the least, and the most frequent were dictionary correlations. So next, we added all of the three schemes together at once and tested this with different sample sizes. So we used sample sizes between 0.5% to 100% of a row group. And the compression ratios ranged between 23% and 26%. So the lower sample sizes lead to less accurate expected compression ratios, which effectively means it makes it harder to find correlations. But even with small sample sizes, we can see that the improvement is actually not that much worse than the best case. So a big reason for how we could achieve these results with small sample sizes is the mechanism of reversing C3 schemes. So if due to inaccurate expected compression ratios, we realize that the real compression ratio of this C3 scheme is much worse than expected, we can cancel the scheme and then use the single column compression schemes instead. And this graph shows the improved compression ratios with the reversing mechanism activated and deactivated. So the lower the sample size, the more C3 schemes are reversed. And from sample sizes of 25% and onwards, the expected compression ratios are accurate enough that reversing is not needed. So until now, we have been compressing only a single row group, but now we move on to compressing multiple row groups. So we used up to 10 row groups per table. We had an average of 9.1, since not all tables had 10 row groups. And so based on the assumption that correlations should hold over the whole entire columns, that means that the correlations we find in one row group should also hold in other row groups. So we tested this by finding correlations in the first row group and reusing the correlations we found for all subsequent row groups. In this case, we don't need to search for correlations from scratch for every new row group. So the first result shown here is the compression ratio improvement when sharing no correlations. That means searching for correlations from scratch for each new row group. Our first method of sharing correlations is to share all correlations that were in the correlation graph for the first row group, and using this as a starting point for finding correlations in the new row group. So for every new row group, the only thing we have to do is update the edge weights and run the greedy algorithm again to pick the best schemes. Our second method of showing correlations is to share only the final schemes used by the first row group. So here we, again, only need to update the edge weights and confirm that this correlation still holds for the new row group. We can see that we lose almost no compression ratio. We have like 1% here. And the second row in the table shows the total number of expected compression ratios that we computed for C3 schemes. And we can see that we can reduce the number of expected compression ratios computed by a factor of almost 10, which is proportional to the number of row groups we used, also 10. So this confirms that correlations can be reused between row groups, and this helps us significantly save on the overhead of finding correlations, while only minimally sacrificing compression ratios. So finally, we can take a look at the compression ratio improvements per table. So this graph shows that the effectiveness of C3 schemes highly depends on whether a table has correlations or not. So for tables with many correlations, we can see that we can improve the compression ratio by over a factor of 2. But our datasets also included many tables which didn't have, or which seem to not have, any correlations. And the results we looked at previously of around 20% improvement were the average over all the tables. Future work in this direction includes, for us, benchmarking the decompression and compression speeds of using our C3 schemes and framework, since this project was mainly focused on finding the best ways of improving compression ratios. And also integrating our C3 schemes into CWI's fast lanes file format. And then, of course, to find and exploit more types of correlations which can be found in other real-world datasets. Thank you for your attention.